Okay, so last class we talked about gear terrains, and we said that the terrains are basically two pairs or more of gears connected to each other, and then to produce a motion. This could be a reduction or increasing of the RPM, and we understand from previous knowledge, and we revise this also with you, that if you have, for example, two gears like the one you see right here, then the RPM of the gear number 3, which is this one, is the ratio of the number of teeth multiplied by the RPM of gear number 2, or this can also be related through the diameters. That's what we said. And we talked about internal. We said that in external, the two gears move in the opposite sense to each other, while in here they both move in the same direction. And then we talked about the terrain value, okay? And for the terrain value, ya shabab, we have here a set of like how many gears? This is N2, that's number 1, 2, 3, 4, and 5. So these are 5 gears starting from gear number 2 until gear number 6. And we said that if you want to know what is the RPM for the last gear, knowing what is happening to the first one, then you multiply it by the ratio, which is N2 divided by N3, multiplied by N3, divided by N4, multiplied by N5, divided by N6, which is basically, this is the terrain value, which is the product of the driving teeth numbers divided by the product of the driven teeth, okay? Now, what you should know is that's something I didn't mention before, is that here, if you really multiply the numbers, one by one, you would see that the number of teeth for gear number 3 is canceled out, which means that this gear, I think it is called idler gear, and gear number 3 is basically like an object just to fill in the gap between from here to there. It's just filling the gap. Its number of teeth is not going to change anything in the motion. You understand that? It's like it doesn't exist. We canceled it out. So this is something I think I forgot to mention, that we talked about the helical gears. Then we also discussed the two-stage compound gear. Now, we have an example here. I'm going to just discuss it quickly, and then we'll talk about more detailed one. In here, for example, let's say this is an assignment for you to design a gearbox. And what it says here is that we need a gearbox that provides 30-to-1 ratio, and with a ±1% increase in speed, while minimizing the overall size of the gearbox. What does minimize mean? What does it mean for you? What is the action that you should do to perform this minimization? Well, the best thing, the best tool, is to take into account or to consider the interference, because the interference, for example, is always telling you that I'm going to let you know what is the minimum number of teeth which will let you avoid the interference. The minimum means that's the smallest. And as we know, if you want to put many, many teeth, you need to increase the diameter of the gear. So this is one way to handle that minimum size. You understand? So it's indirect. And so what are we going to do? Considering that we have the arrangement of a compounded gearbox, then we see here that we have 3 shafts. This is gear number 2, and this is 3, and then this is 4, and then this is 5, for example. All right. Now, if we imagine that the gear terrain value is we said that E, ya shabab, is the multiplication of, for example, 2, 3, and then 4 and 5, kind of. It's the multiplication of the gear ratio, 2 gear ratio. So if you assume, just as a first approximation, that this gear ratio, this one is the same as this one, although you don't have to. You don't have to maintain this. The gear ratio can be different from one set to another. But just as a starting point, if you say, I want them to be the same, then basically this 30 is going to be equal to the square root of n, let's say a over nb squared. Why? Because if they're both the same, then you will have one ratio, you multiply it together, you get a square. And thus, if you want to know this ratio NA over NP, then it's going to be the square root of 30. So that's a simple way. And then when you get the square root of 30, you get how much? You get 5.47. So you can say, okay, I am right there. I need a ratio of nearly 5 for each one, and then I will be near the 30-to-1 gear ratio. You understand? So it's just, this is just playing around. Now, how do you know what is the smallest number of teeth? Well, this, considering that this is a helical gear, all right, then we can use the equation with M. Do you remember the equation which needs M, which needs K, and it needs the pressure angle phi? If we put all of these, we will get the NP, which is the minimum number of teeth for a pinion. Okay, the minimum number of teeth for a pinion. And that minimum number will guide us to be in the low side because it's minimum. So if you put this like a pressure angle 20, and then we have K equals to 1, and then a gear ratio of around 5 or 6 in that range, you will end up reaching an approximate number for avoiding interference, which is around 16. So if that is 16, it means that NP is 16. And if NP is 16, then N2 over N3. Now look, ya shabab, this is the smallest guide. So this is the pinion, and this one is the gear. When you found NP, it means you just determined the number, the smallest number of teeth for NP. And that means that the ratio here is going to be 16, which means that N2 is going to be equals to N3 multiplied by 16. Now, what is what that will give you? It will give you an approximate. You will know approximately what is the size of the gear. Now, just remember that we are assuming here that the ratio is the same, and by doing so, we will end up having the number of teeth for the gear, not the pinion, equals to 88. So if you have 88 divided by 16, and then 88 divided by 16, that's the reason why we have this twice, because we assume that the ratio between the two gears is the same. And this is gonna give you how much? 30.25. So what does this mean? It means if you decided that you have the number of teeth here as 16, and this one as 88, this one is 16, and this one is 88, then you will have an output of a ratio of 1 to 30. Your speed, if you put 1 RPM, you will get 30.
Doctor,
That's the mean.
For calculating the number of teeth, where was M obtained from? There's the formula. Yeah, the formula includes M and
the
fire.
M is the gear. The M is the gear ratio. That's where the assumption of equal. This is M. Isn't that true? We said that N, or let's say NA over NB multiplied by NA over NB is equal to what? We said that this is supposed to be E. And we said that E here is 30. So because it's the how much is the amplification of the rotation. So it's 30. So this one now is squared, forget about this. And then you get the ratio as the square root, which is NA over NB equals to the square root of. So this is M now. M will be the square root of 30. This is just a rough estimation. What you have here is that with a little tricks, you were able to give us an approximate number of, number of teeth for a gearbox that deliver nearly 30 to 1 RPM. Now,
but before doing the calculations, they've provided the interference. It says the minimum number of teeth to avoid interference is 16, right? Is that given, or do we calculate it from the things provided?
This one, Hassan, that's what I said. I said you go to this equation.
Yeah, this equation, but seems like phi isn't provided. And
over here.
Yeah, but some of these things haven't been provided in the equation, right?
What is it?
Or in the example. Some of these things haven't been provided in the example, right?
Exactly. Like, for example, it didn't mention K, so we'll assume it to be 1. And we will take a typical helix angle as well as a 20 pressure angle. You understand?
Okay. Yeah.
So what happened over here is that this example is intentionally made not to give you too much information. Is it trying to teach you that with a minimal number, just by, honestly, the truth is, it didn't even tell us that this is a helical gear. It's just in the solution says that we're going to use this figure, which is this one. So we assumed it to be helical. It wasn't the best example. But what I'm trying to tell you here is that even though, let's say, Shabab, that you were in an industrial project and somebody told you, I want a gearbox right now, 30 to 1. You can just ask, let's assume it's a spur gear. If it is a spur gear, the pressure angle is 20. The equation for NP for a spur gear, you remember it? It's almost the same as helical.
Because the equation
it's almost the same as helical.
Yeah, the equation they've recommended is from the spur gear section 13-7.
It's 13-11.
Yeah, no, the equation is 13-11, but it's from the interference section, and they were focused on the spur gears there.
So maybe, yeah. Then maybe, yeah, maybe. Oh, but let me see. This is the bad thing about the book. Figure number, can you check if you go back? This is the problem. If you go back to figure 1328, it's not a spur gear. But
okay.
maybe Hassan, maybe you're right. Maybe this is the problem with the textbook. Maybe it was solved for a spur gear, but they are telling us that the arrangement arrangement of the gearing. It's true in the sense that this gear thing doesn't have to be helical. This can be done with a spur gear. Okay, so it doesn't matter. That's what I want you to know. What I want you to know is that in P, okay, in exam, you will be exactly given what you need to. But in industry, you just ask the question, guys, do you want a helical gear or a spur gear? And from that, you will know the equation, the appropriate equation for NP, which is the smallest number without interference. And if you use the spur gear one, that's fine. This means that you are following the spur gear. What is interesting here is this. As first approximation, you went ahead and you assumed a constant ratio. So this set will provide N1 over N2 the same as this one. This is just an assumption. And let me move on to the next example. In the next example, you're right. I think it is solved for a spur gear. It is not, this is very confusing, but you're right. So what happened over here? Look at the other example. This is a little bit better in the sense that the example says, I want an exact 30-to-1 gear ratio. Exact. It doesn't, look, this one, we ended up with 30.25. Now, Shabab, this is very funny. Why? Because if you do not deliver the ratio, it means that you are, it's just like as an example, just like telling people your car is moving with a speed of 100, but then you pass through Sahar radar and then it catches you. Why? Because it was actually faster. Do you understand? So, of course, we don't allow this. So here in this example, it says, no, we want an exact ratio. So the ratio here, how are we going to get it? There is a bit of an assumption. You have to do it. So assuming that this is a spur gear, I think this is very important note. Thank you, Ya Hassan. I'm going to write this note in the slide that this is a spur gear. It's not a helical gear. Okay? So if that's so, then now we know that E is equals to 30. So look what the solution did. He said, okay, how can I get exactly 60? 30. Well, in the past example, we knew that square root of 30, which indicates that the ratio is the same, is around 5.4. So he said, I don't like fractions. How about multiplying 5 by 6? Huh? Not bad. Not bad. So what will happen? You will assume that the gear ratio, the first one, is 6, and the second gear ratio is 5. A neat assumption. And it is not like, oh, what if he did more? What if he, no. What other multipliers? You will multiply how much? 2 by 15? Come on. 2, the gear ratio 2 by 15. So they should be close to each other, not too far, not too much far from each other. So we have, so we assume that 2, this is 2, this is 3, this is 4, and this is 5. So 2 over 3 is equals to 6. And we assume that n over 5, n4 over 5 over n5 is equals to 5. Now, look what happened. By knowing the gear ratio exactly, I can go to the first set and say, all right, this is the first set. I know what is n2 over n3. Actually, I should know what is n3 over n5 because the gear ratio m is n for the gear over n for the pinion. All right? So look, I brought the equation right here for you. I don't know K, I will assume it to be full. And I will assume a standard pressure angle of 20. Okay, and M, I already know it. It is 1/6. Good. So if I do this, I will know what is exactly the number of teeth for the pinion, which is this guy. So I calculated this, and I got this guy 16 again. 16. So if I know that this is 16, then N2 over 16 is equals to 6, which means I can find 6 by 16. All right, this is going to give me 96. There it is. And now, taking this as the minimum, all right, I can also assume that the other set has a pinion and a gear, right? So assuming that this one, the smallest one, will have the minimum of 16, then I multiply it by 5, which is the ratio, to get the number of teeth for gear number 4, this one, which is how much? 80. So now I got an exact value of 96 divided by 16 multiplied by 80 divided by 16, which is exactly 6 multiplied by 5, which is exactly 30.
Doctor,
Yes.
why are pinions have the same number of teeth?
The pinions?
Yes.
Well, if you go and look, K is the same, phi is the same. The ratio M is coming from the 6 and 5, and they are not very much different. So you might get for the first one like 16.1, the other one like 15.9 or something like that. So you will find that 16 is the closest value. This is due to the fact that M is very close. You understand? You got that?
Yes.
So remember, we are not inventing NP. We are calculating it to avoid interference using this equation. Good? Okay. Now look what happened. The story didn't end yet. Now what do we have? We have the same exact problem, but for some reason, the client demanded inline configuration. What is inline configuration? If you go back to this, you will see that we have actually 3 shafts. The first shaft is this one. The second shaft is this one. And then the third one is this. You get that? So the client came to you and say, no, this is going to make my, the gearbox is a little bit spacious here. It's too big. I want the 2, look, this is shaft number 1, this is shaft number 2, and this is shaft number 3. Do you see? The green and the blue are in line. Now, the first thing that will happen here, and it's very interesting, it's geometry again. Mechanical engineering is a lot about geometry. So what happens here? You cannot just ignore the fact that this condition of alignment, okay, will mandate that half of the gear, which is diameter, which is the radius here, and this one must be the same. If I add the red and the black here, and the red and the black here, they must be the same. Isn't that logical, Yashaban? The distance is the same. They must be. There's no other choice. Now, automatically, this will give you this equation that the diameter over 2, which is the radius, for gear number 2 and for gear number 3, if you add them, they are equal to the sum of gear number 5 and gear number 4, which means you can actually convert this into a relation for the number of teeth, and then you will end up with the number of teeth for 2 and 3 is the same as the sum of the number of teeth for 4 and 5.
Doctor, what's different about reverted gear train? Is it just that it's in line?
Yes, this is the inline. It is sometimes called the reverted gear. Okay.
Okay.
All right. Now, let's see how are we gonna solve this. Now, again, we say, okay, we will assume that the ratio N2 over N3 equals to 6, just like the previous one. N4 over N5 is equals to 5. And now we have a third equation to satisfy. Good. So let's see. If we go back to the same story, we will come back to N3 having the smallest number of teeth, which is equals to 60. The number of the count, teeth count. So if that happened, then I know, just we did it before, that 16 by 6, the ratio is equals to 96. Good. But this time, look what happened. When I know that N2 is equals to 96, and I know that N3 is equals to 16, then I have to add them. And this is going to add up to 112. And when I add them up, I would say that this 112, it must be the same sum as for N4 plus N5. So what happened here is that I know that N4 over N5 is equals to 5, which means that N4 is equal to 5 multiplied by N5, which means if I substitute this in here, I will end up with this equation, which is 112 equals to 6 N5. So if I divide 112 by 6, I will get N5 as 18.67. Once I saw that fraction, I know I'm in trouble. I can't. This is the number of teeth. I can't have fractions. So what can I do? So what are we going to do? We say, okay. We don't need to continue. We're in trouble here. We are not going to obtain an exact ratio. There is a little fraction, so it's not going to work out. So the solution of the book says, okay, how about if we normalize the problem in the sense that we will assume, very funny, but we will assume that gear number 3 has 1 tooth. I want to see what the others will have. And when I start by 1, and automatically the second one become a multiple, and the third one a multiple, and the fourth one is a multiple, I can easily identify how much I can multiply 1 by, and then the other will follow. That's the trick. So if we do this, we will end up with N2 divided by N3, which is equals to 6. The ratio is the same, but as N3 is equals to 1, I will end up with N2 equals to 6. So funny, but it's fine. This is just, we are trying to investigate the whole thing. Why? The other way to do it is to keep guessing. Say, okay, let me make it 17, and the other one 16, and the other one 18. Oh, it doesn't work. Let me repeat again. So you will get tired. You will see that there might be in some cases a fraction of 0.01 coming. and it will ruin all of your calculation. So instead of doing so, let's make it clean. Now, if we do this, we can add n2 plus n3, which is equal to 6 plus 1, which is equals to 7. Right? Now, look what happened. If I do that, I know that n4 divided by n5 is equals to 5. I'm still loving these ratios. I like them. I'm not going to change them. And I'm still going to have n4 equals to 5 in 5, which means 7 is equal to 6 in 5. And now look what happened. I got n5 equals to 7 divided by 6. Now, I don't like the 6 down there. So what I'm going to do, I say, let me multiply by 6. Let me multiply by 6. And if I multiply by 6, I'll get rid of it there. Yeah. So if I multiply by 6, what would I get? I will understand basically that the gear number 3, the first binion has to be a multiple of 6. That's the meaning, because 1 didn't work. I need to multiply it by 6. Now, remember, 6 is a small, okay? And 6 is below 16, which means I will not avoid interference. So, what is the multiple? The nearest multiple of 6, which is above 16. It must be above 16. If it is less than 16, I will have interference. So I need to go up, but I don't need to go up a lot. I just need to, because I still have the condition to minimize the gearbox size. So the first multiple of 6 is 18. Isn't that true? 18. Right. So I would say that N3 is equals to 18, which means that N2 is equal to 18 multiplied by 6, which is going to give me 108. And I will have 108 plus 18, which is equal to N4 plus N5. I repeat the same process. I get N5 is equal to the 126, which is the sum, divided by 6, and I got 21. Very beautiful. And then I get N4, which is 105. So once I get those integers, I get this, 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 and this. Now, if I get the train value, which is 108 for gear number.
Why didn't they use 12? Because 12 is also a multiple of 6, right?
Yeah, but I told you, it will drop me below the threshold value of the interference. The solution is bounded. So that's what I want you to feel comfortable with. It is not open to the sky. Huh? It's not like sky is your limit and, oh, I am confused, I don't know what to do. Actually, you bounded the solution. The first time you decided that the ratios are 5 and 6. Automatically, you are just around there. As you see, just by using almost the same ratio, the numbers keeps coming again. You understand? So, and by the way, you got the ratio exactly 30, and you got this satisfied as well. 126 equals 126. All right. So this is good enough for that type of gear terrain. Now we are going to talk about the planetary gear. The planetary gear, ya shabab, is a different way of gear terrain, and it is very, very, very important. Why? Because it is in the heart of the automatic gears for automobile. Now, I'm going to ask you this. Do you know that there is cars with manual gear?
Yeah.
Did you drive one before? Anyone?
Yes.
Is it that true, ya Muayyad? You know how to drive it?
Yes.
How about the rest?
Not me.
Oh yeah. Anybody else? Come on, be courageous. Tell us that you don't know how to drive a manual gear car. Most important thing is I know. That's it. So what happened is that the automatic gear is a marvel by all means. I mean, I'm gonna show you. I don't have the. I tried it with the other section. It didn't work out. So I'm gonna share with you in the chat. Just wait a second. Don't watch it right now, ya shabab. We will watch it after the class, inshallah. But this is gonna show you how do we use a planetary gearing to stack actually multiple ones, which is gonna make it so complex in order to have this fancy automatic gearing in the car. The manual is different. There are a set of gears, and then there is the pinion, and the pinion moves, and then get engaged with different gears, and that's how we shift from 1 to 2 to 3 to 4 and 5. But this one is way more fancy. And the interesting part is that we actually, in cars, they stack multiple ones. So you just head will blow up. But of course, if you get a job in Toyota or BM or something, you will love it. It is very complex, but you will love it because it is going to maybe be your specialty and you will like doing it and you will be expert and so on and so on. So what is the story of a planetary gear? Well, the story is that it has usually a gear in the middle, which is called the sun gear. It's just like, I think it is driven from the analogy, like a solar system. And then we have a planet gear. There it is. That's like revolving around the sun. And then we have the ring gear, which is like the outer cloud, or the boundary of the solar system. So what happened here is this. There is an arm which is connecting this. Now the interesting part come here. You can actually fix this guy. Of course, each one has different number of teeth. And we have the arm, which is not teeth, it's just an arm. So what happened? You can imagine that the sun gear can rotate, and then this gear will revolve like that. Or you can actually fix the sun gear, and then and fix the arm, and then what will happen is that this is gonna rotate, and this outer ring is gonna rotate with it. I mean, it's not easy maybe to visualize, but you can have all sorts of motion. You can fix one and the other rotate. You can fix one and the other rotate. And by doing so, you can get different reductions. So all what you need to do, and we will see it in the video, is that the engagement of different elements. You fix this, you rotate the other. You fix this, you rotate the other. That's how you get the ratio, the reductions that you want. All right. So I'm gonna quickly, just for 1 second, share my slide here, just at least you see this animation quickly. There's no point of showing you the video, so this is how it works. Now, if you look here, the red one is kind of the sun. These one are the planets, and this is the ring. Now look, this one, the blue one rotate, the red one rotate. This is fixed, and you can have other ways to configure the motion in the way you want. All right. So let me go back to my slide, and I am going to. Where is it? Oh no. Okay. So what happens here is that if we make a very simplistic arrangement where we have gear number 2, okay, and then we have gear number 4, like here, and then this is gear number 5, okay, and we have an arm, and we will call the arm number 3. Then if we measure the relative velocity of gear number 2 with respect to the arm, then this is the relative RPM contour. Then it is equals to the RPM of the gear into minus the RPM of the arm. If we do the same between 5 and 3, which is the arm, then we will get N5 minus N3. And now if we take the ratio, we will end up with N5,3 and N2,3. Now, this reminds you, we forget about this side, forget about it. But the left-hand side reminds you of what, ya shabab? Of the relation between the first gear and the last gear, okay? Since the arm doesn't have teeth, and we are only here talking about its rotation. Now, so what we can do, we can actually, ya shabab, think of this as I told you, as the RPM of the first and the last, and which is the same as the gear terrain value. So, which means that we can have E over here, which is equals to N5 minus N3 divided by N2 minus N3. Now we know that N5 is the last gear over here. This is the last one. And we know that NA is what, ya shabab? It is the arm. And NF is the first. And this one is NA again. So as it says here, we have NF is the RPM of the first gear in the planetary train. NL is the last gear in the planetary train. And NA is the rotation of the arm. Okay? Now, what we can do, so we're going to start this example, but we will probably not finish it. So in this example, what do we have? We have the same arrangement as this one, okay? So what do we have? We have here the ring, which is named number 5, and it has number of teeth, which is 80. And then we have the sun gear, which is number 2, and it has 20 teeth. And then we have the planet gear, which is number 4, and it is called and it has 30 teeth. And of course, the arm is number 3. Now, what does this question ask about? It says the sun gear is the input. So the input is coming from the sun gear, okay? And the sun gear rotate clockwise like this, all right, with an RPM of 100 revolution per minute. If we consider a right-handed coordinate system, this means that any rotation which is counterclockwise is positive, any rotation which is clockwise is negative. And that's why we are going to say that N first, which is N2, is equals to minus 100 revolution per minute. Okay? All right, ya shabab. Then we have the last gear, okay, which is N5. That's the last gear. So N5 here is L, which is N5, which is equals to 0. Why? Because it says that the ring gear is held stationary by being fastened to the frame. Good. Now we want to find the RPM, the speed for
Okay,
the
which one is the
arm.
ring gear?
This one. It's written over
Oh,
here.
okay, right. I thought it was the
Okay. We want to find the RPM for the arm as well as gear number 4. That's what we want. So I'm gonna continue this in the next class. I will have to stop taking attendance right now. This, okay, Yusuf.
Yes, here.
Majid Al-Abbad.
Yes, I am here.
Hassan Ayash.
Yes, I'm here.
Abdul Rahman.
Yes.
Muhammad.
Yes.
Abdul Aziz.
Yes.
Ahmed.
موجود دكتور.
Abdullah.
Yes.
Khalid.
Yes.
Maslih.
Yes, doctor.
Saud.
Yes.
Abdullah.
Yes.
Salman.
موجود.
طارق.
موجود يا دكتور. موجود يس.
مصطفى. ويسر. علي العمر.
موجود دكتور.
حسام.
موجود يا دكتور.
هاشم.
موجود.
سلطان الحربي.
موجود دكتور.
نايف.
موجود دكتور.
محمد.
Yes, دكتور.
عبد الله.
Yes.
مشعل.
موجود.
انت جعفر.
Yes.
خالد.
موجود دكتور.
مؤيد.
حاضر.
علي.
Present.
and Hassan.
yes here.
That's everybody. All right يا شباب. See you next class.